Okay, so now let's try to write down some concrete results. We're not going to derive them. This is again things that we studied last year. Okay, and you can look them up in any book. So we'll say at one loop. So what does it mean to work to one loop? It means when you calculate G4 prime, you'll only work to one loop. And when you calculate the 2-point function, you only work to one loop. Okay, so when we calculate both of these to one loop, we find that the anomalous dimension vanishes. So there's no anomalous dimension at one loop. And this just reflects the fact that there is no wave function renormalization. So the anomalous dimension is always driven by wave function renormalization. And because there's no wave function renormalization at one loop, it means that there's no anomalous dimension. But we also calculated the beta function to one loop. And what we found that the beta function was 3 times g squared divided by 16 pi squared. So this is greater than 0. And so then we studied the running coupling. And so let's say the running coupling. And we denoted the running coupling by G bar. And the equation that we solved was dg bar d log p over m. So what is this equal to? Well, this is equal to the beta function, which is 3 g bar squared over 16 pi squared. And then we can imagine that this change over here in the coupling is because of dependence on m. So in that case, we can write this as, so this is just some simple calculus, dg bar dm. Okay, so why is the coupling changing? It's changing because we're changing the scale m. Sorry. So check this, please. This should be equal to minus m dg bar dm. So while we can very easily solve this differential equation, it's not a difficult differential equation to solve. And what you find is, so we can then plot the running coupling. There it is, G bar. And on this axis, we can plot the log of P over M. Or you can plot P over M itself. This is monotonic correction. And what we find is whatever coupling you start off with in the UV, you flow towards 0. So if you flow towards 0, you would call this an irrelevant coupling. Now, in our case here, you'll probably remember that because in D is equal to 4, G was dimensionless. That means that this running is coming completely from interactions. If you had just done dimensional analysis, you would have said that this coupling was marginal. So the way that we describe this coupling is we say it is marginally irrelevant. Okay? And this flow is being driven completely by quantum effects, by interactions. Good. So now to give you an idea, let's just record that in 4 dimensions, G was length to the naught. Actually, in 3 dimensions, so I want you to check this. We can easily check that G was length to the -1. And in 5 dimensions, you can check that G is length to the +1. So what does this mean? In 3 dimensions, because G is an inverse length, it means that this coupling is relevant. In 4 dimensions, this coupling is marginal, and in 5 dimensions, it is irrelevant. So if we lower the number of dimensions, we tend to make couplings more relevant. Now notice that our interactions give us a beta function which is positive, and that's why the coupling became irrelevant. But if we go below 3 dimensions, just because the coupling now gets a negative length dimension, dimensional analysis will tend to make the coupling relevant. So the idea that Wilson and Fisher had, and this is a brilliant idea, is that maybe we can cancel the tendencies of interactions to decrease the size of the coupling with the effect of changing the dimension to less than 4 dimensions, which tries to increase the coupling. So what Wilson and Fisher did, so now we're actually reviewing the Wilson-Fisher idea. They said, work in 4 minus epsilon dimensions, and we will leave epsilon to be a free parameter for now. We'll solve for it. We'll see whatever it needs to be. Well, in 4 minus epsilon dimensions, what does the action look like? Well, it will be an integral over d4 minus epsilon x. We'll have a 1/2 d mu phi, and we'll have plus g phi to the 4. So if we look at this first term over here, let's look at this first term. We know the action must be dimensionless. So from the d4 minus epsilon x, so from the measure, we've got a length to the 4 minus epsilon, okay? So this really comes just from the measure term. That's where we're getting this from. Then we've got a length to the minus 2. That's coming from these two derivatives, the d mu phi, each of those is a length to the minus 1. And then we've got the dimension of phi squared, and this must be length to the naught because the action is dimensionless. So what is phi squared equal to? Well, this is easy to get. This is L to the epsilon minus 2. And so we can now work out what is the dimensions of phi itself. Dimension of phi will be L to the epsilon over 2 minus 1. Good. Now with this result, we can now analyze this last term in the action. So this term must also be dimensionless. So we've got an L to the 4 minus epsilon from the measure as usual. Then we've got the dimension of G. So let me call this G tilde for now. You'll see why in a minute. Let's maybe change that. This is G tilde, good. And then we've got phi to the 4. So what's the dimension of phi to the 4? Well, this will be length raised to the power of 4. It will be 2 epsilon minus 4. And again, this is a term in the action, so it has to be dimensionless. So now solving, we very easily get that the dimensions of G tilde, well, the plus 4 and the minus 4 cancel. The 2 epsilon minus epsilon gives us an epsilon. Take it over to the other side, and we've got a length to the minus epsilon. So now it's a negative length dimension. So dimensional analysis will make this coupling grow. And we can tune how much this coupling grows by changing epsilon. And if we pick epsilon just right, we can exactly cancel the effect of the interactions, which are trying to make epsilon smaller. Now, the price that we've had to pay is that we now need to work in epsilon dimensions, and epsilon need, in 4 minus epsilon dimensions, and epsilon need not be an integer. So let's say that epsilon is equal to 0.01, for example. That's a small value of epsilon. Then we would be working in 3.99 dimensions. Now, what exactly does it mean to work in 3.99 dimensions? What's the conformal group in 3.99 dimensions? Well, these are great questions, and these are topics of current research. We're not going to ask questions like that. We're just going to accept that everything makes sense and that we can take epsilon to be non-integer, and see where that leads us. This is the logic that led Wilson and Fisher to their CFT. We'll continue in a moment.